Well, welcome again to our journey into algebra and number theory. And in the previous recording we showed how we could take the Zn groups and we could factorize them, as we saw here, provided the numbers are relatively a pairwise co-prime. Then we could factor Zn into a direct sum of these additive groups. Now that's a very nice result from group theory, but it's got a very nice, even nicer application to number theory. And so in fact we're going to get a little proof, a very simple proof, using this idea of what is known as the Chinese remainder theorem in number theory. This actually does go back to the Chinese. They were the first to, we believe, to have been solving these, or equivalents of, they wouldn't have written it like this, but the equivalents of these linear congruences. So here's a simple example of this. We want an x, so we want to find an x that leaves a remainder of 1 when I divide it by 3. The same x has got to leave a remainder of 3 when I divide it by 4, and the same x has got to leave a remainder of 2 when I divide it by 5. And we want to know, firstly, is there such an x? What are the conditions on the moduli for such an x to exist, and then how do we actually find this value of x? Now we can interpret this in terms of group theory by thinking about this right hand side, 1, 3, 2. We can put this as a triple and think of this as an element in Z3 direct sum Z4 direct sum Z5. Now we know that this direct sum is isomorphic to Z sub 60. That is, there's a bijection between Z sub 60 and this one. And so what we're looking for is we want the inverse under this bijection of this element 1, 3, 2, and that will give us our x. So to solve this problem we need to find a unique element in Z60 which corresponds to or maps across to this in this set. Now unfortunately, although such a isomorphism psi, we showed before that it is 1 to 1 and onto, so it must have an inverse. However, the inverse is hard to write down, and so that's difficult. Nevertheless, the fact that this psi does have an inverse is enough at least to guarantee that the system does have a unique solution modulo 60. And that statement of that is called the Chinese remainder theorem. And so here are the ingredients. We take A1 up to AT, which are pairwise relatively prime moduli, and we want an x that's congruent to B1 mod A1, B2 mod A2, and so on down to BT mod AT. Then the Chinese remainder theorem says there exists a unique value C, so that x is congruent to C modulo the product of all these moduli. And the proof of this is remarkably simple now that we've got this group theoretic machinery, because we know that Z sub A1 through to AT is isomorphic to these this direct sum, and that means if I take a B1 up to BT in this side here, then there is, because there's an isomorphism between the two, that will map to a unique element C in this side. And that's it. And that's the proof of the theorem. Now, although it's an existence theorem, so although the proof guarantees a unique solution modulo A1 up to AT, the proof doesn't actually tell us how to calculate C. It's one of those existence proofs, but doesn't actually give you the method. Now there are several methods for solving systems of linear congruence equations. I'm just going to present one of them, which is probably my favourite. Now that we have the Chinese remainder theorem, we know there is a unique solution, then I want a nice, fairly simple, quick way of writing down what the solution is. So I'm going to do this on a separate page here, just to put a bit more detail in. So here's the example. I've got x is 1 mod 3, x is 3 mod 4, x is 2 mod 5. Now the Chinese remainder theorem guarantees there is a solution modulo the product of these, which is 60, and I'm going to just write it down. in some sense. So here's what I do. I take x is congruent to 1, so that 1 is the one here, plus 3 times alpha. The 3 comes from this first modulus. 3 times, I'm not telling you what alpha is yet, 3 times alpha. And then I multiply 3 times 4 is 12, and I put plus 12 beta, modulo 60. So I'm introducing these two parameters here that I'm going to calculate. If you've got more than 3 congruences, well, that's okay. The method just generalizes. You take this one plus 3, this one times alpha plus the product of these times beta plus the product of these times gamma, and so on, where you have one less parameter than there are equations. Now, by the way, equation 1 is automatically satisfied, because if you read this modulo 3, then this is 0. So you just get x is 1 mod 3. If you substitute this now into equation 2, then equation 2 is working mod 4, so mod 4 12 is 0. You see why we did this construction in the first place. This is 0. So I just get 1 plus 3 alpha is 3 mod 4. And I'm going to work out what alpha is. This is a nice simple linear congruence now. So what did I do here? I subtracted 1 from both sides. I note that 3 is the same as minus 1 mod 4. And then I can say then alpha is just minus 2, which is 2 mod 4. So I'll take alpha to be 2. So I plug that back up into my x here. So I get 6 plus 1 is 7 plus 12 beta, and plug that into the equation 3. So at the moment I've got x is 7 plus 12 beta mod 60, plug it into equation 3, gives 7 plus 12 beta is 2 mod 5, and 7 minus 2 is 5, which is 0 mod 5, and 12 is 2. So I'm going to take beta to be 0, and plug that back into here, and I just get x is 7 mod 60. And by the way, we can check our solution makes sense. If I read this modulo 3, I get 1. If I read it modulo 4, I get 3. Read it modulo 5, you get 2, and they were the original equations. Well, what happens if the moduli are not pairwise co-prime? Well, then we have to do a little bit more work on it to make sure that we can reduce this down to a consistent system. So just as another example here, I've got 1 mod 3, 3 mod 5, 7 mod 12, 7 mod 8. So I'm going to take this equation 3 here. 12 is 4 times 3. So I'm going to read this modulo 3, and I'm going to read it modulo 4. So modulo 3, I get x is 1 mod 3. Well, I knew that. That was equation 1, so that's happy. That's consistent. And I already have that built into the system of equations. Reading it modulo 4, I get 3 mod 4. Now on the other hand, 7 mod 8, if I read this modulo 4, I also get 3. So if x is 7 mod 8, then that implies x is 3 mod 4. Not the other way around, of course. And that tells me that the system then is consistent. The system is consistent, and I can replace replace these two, because I've already got the 1 mod 3 up here. I can ignore this one here and just take this one here. So the system is consistent, and I can rewrite it then as x is 1 mod 3, 3 mod 5, 7 mod 8, and these are all pairwise co-prime. So the solution, again, I'm just going to write down. We know there's a unique solution modulo the product of these three, which is 120. And again, so I have x is congruent to 1, plus 3 alpha, plus 3 5s of 15 beta, and the answer is unique modulo 120. And once again, I plug this into equation 1, is happy, into equation 2. This is 0 mod 5, so I just get 1 plus 3 alpha is 3 mod 5. Subtract 1 from both sides, and again I note that I double both sides here, so 3 2s are 1 and 2 2s are 4, so take alpha to be 4. put that back up into alpha as 4 back up into here and go to equation 3. So I get 1 plus 12 plus 15b to 7 mod 8. 15 is the same as minus 1, and if I take these two on the other side, I get negative 6, so take beta to be 6. So plug that back into the formula for x, and we end up with 103 modulo 120. So that's a nice application of the abstract algebra back to the number theory, and that's what we just saw here. There was a unique solution to that system. It was 103 mod 20. So I'm now going to return to the problem of decomposing these U groups into direct products. So far we've only just looked at that very just by example, but I want to keep in mind the comments made about direct sums. And it's going to turn out, in fact, that the results we got for the direct sums actually help us to analyse the U groups. So firstly, I'm going to note that the isomorphism psi that we use to prove this result also preserves multiplication in ZAB. Since if we take psi of x to map across into ZA direct sum ZB to be that, then psi of xy is just xy times 1a, xy times 1b. Remember what these mean. This means I read xy modulo a, this means I read xy modulo b. And I can split this ordered pair up into a product of ordered pairs, and that's psi of x, psi of y. So although psi was an isomorphism that was acting on these groups additively, it also turns out to preserve multiplication if we're now thinking of this as a ring. And I can use this now to prove our main theorem here, Theorem 5, that says that if a and b are integers that are relatively prime, then the U group UAB is isomorphic to U sub A direct product U sub B, as we might have hoped. So graphically I'm thinking of it like this. Here's my ring. I'm now going to think of this ZAB as a ring, and there's my ring ZA direct sum ZB, and we have an isomorphism between these two now if A and B are relatively prime. And living inside this ring is the group of units, and over here there's the group of units in these two, or the direct product of the group of units here. And I claim that this isomorphism psi, which worked additively, also works multiplicatively, and it's going to preserve the units here get mapped to the units in here. And that is going to be sufficient to show the result. So here's the proof of this, which is a little bit technical but not too hard to follow, I hope. If we now think of Zm as a ring, that is with addition and multiplication, we claim that this psi mapping carries the set of units in ZAB to the set of units in ZA direct sum ZB. If this is so, then that's the result. That's the result follows. So if x is a unit in Z of AB, then we're going to show it's a unit over here. So that means there exists an x dashed in here, so that x dashed is 1. Now looking at the image of these points under psi, we now use this bijection, we see that if I take x mod A, x mod B, take that ordered pair, multiply it by x dashed mod A, x dashed mod B, where x and x dashed are the numbers here, then of course I get x dashed mod A, so that's the identity modulo in the ZA group, and multiplying these ones I get x dashed mod B, which is the identity in the second group. So that means that this object here has an inverse, and therefore it's a unit. So if we start off with a unit x in this set, then we end up with it maps to a unit here. Conversely, we now want to show all the units here came from units here. So if we take yz to be a unit in this direct sum, since psi is onto, then there's got to be an x back in the original set, so psi of x gives us this ordered pair. Now that means that x modulo a is y, and that means that x and y are congruent modulo a. Now y is a unit in ZA, and that means it's relatively prime to A, so the GCD of y and a is 1, and hence from this tells us that x and a are relatively prime. Now we do exactly the same argument on xb, and we find that they're relatively prime. And so if x and a are relatively prime and x and b are relatively prime, then x is relatively prime to AB. And that means that x is a unit in ZAB. Thus, there is a bijection. This psi then is a bijection between the units in the two rings. So a little example here now, U10. 10 is the numbers that are less and relatively prime to 10, 1, 3, 7, 9. And the 10 is 2 times 5, relatively prime moduli, so I can factor this 1 into here. And of course, this I can write U1, of course, is just the trivial group here, U5, and that's U5. So that tells me then that the U10 is isomorphic to U5. Final example for this section. So U21, which consists of all the numbers relatively prime to 21, there they are. And 21 is 3b7, so I can factor this as 3 times 7. Now U3 is a cyclic group of order 2, U7 cyclic group of order 6, because these are prime. And in fact then I can then, to find explicitly what the subgroups are, I just needed an element of order 2, so I may as well take 20, which is minus 1. And then I need an element of order 6. Well, 2 did the trick, so 2 2s are 4, 2s are 8, 2s are 16, 2s are 11, my 21, and you double it, you get back to 1 again. And so I got these in fact by trial and error, but the main part of the result is that U21 we can now factor into U3 cross U7. And we're going to see the implications of this back in number theory in the next video.